cool. So now I can tell it correctly. So the library is called Hystrix. It comes from Netflix. It's open source. And the basic idea behind it is that it isolates your application from your dependencies so that if you depend on other systems, other APIs, typically over network or over some other untrusted media, Hystrix tries to shield you from failures in these systems so that your application keeps running even though the dependencies are failing in one way or the other. So I have a bad news for you. This is the end of my presentation, or actually it's the last slide, because we're just going to be looking at code today. So I just have a mic, so that's going to be a really painful one, but still. OK, so I'm just going to be showing you code today, and this is going to be purely coding advantage today. So here I have a piece of code. I'm going to be doing coding with just one hand, so it's going to be slightly slow. Sorry for that. It doesn't particularly matter what it does. The basic idea is that I'm running a piece of code. By the way, is font size OK? I mean, again, there's not going to be any slides, so you should definitely see source code. If it's too low, I can just like scroll it up. So there's nothing inherently wrong with this piece of code. The basic idea is that I'm just like going to the internet, fetching some resource, and reading it. By the way, it's a very poor test case. It's not really meant to be testing anything. It's just a matter of like running a code during the presentation. So there's nothing inherently wrong with this code. And it works on my machine, it works on test environments, and it works on production most of the time, or actually like 99.9% of the times. However, imagine that example.com and replace it with your database, replace it with Facebook API, replace it with another microservice that you are calling. Imagine that one day this service starts failing, and there are many ways in which it can fail. You might have problems with DNS, with router. You might have problems with internet connection, with disk space, whatever. The basic idea is that something that you depend on, that you used to depend on, suddenly starts failing. And there are two ways in which it can fail. It can fail by throwing an exception, or it can fail by just not doing anything. And this is actually the worst case, the worst thing that can happen. You are calling someone, and this other side actually like accepted the connection, so it seems like it's working. However, it just like you just have to wait forever until you get the actual response. So it just keeps waiting and waiting and waiting, and your thread is blocked. And more threads in your application became blocked, and suddenly it's your application that becomes slow. And you can just iteratively apply the same pattern, because now you are the dependency of someone else, and it's that other system that becomes slow. So suddenly, a single failure in one component propagates to the whole distributed system. And this is really painful. So Hystrix tries to avoid this situation, but let's get first into some simpler examples. So what you can do, by the way, with this code, you have a blocking method call that you have like no idea about what it's doing underneath. But you would have to somehow like cap the total time it executes. You would like to apply some timeout. You would like to make sure that calling example.com will not take more than some fixed amount of time. What you can do. And by the way, I want this talk to be like rather interactive, so feel free to ask questions. We're going to run a lot of demos. So if you want to experiment, if you're not sure how things work, just let me know. So again, the question is what you can do with this code in like the simplest use case. Nothing really? Yeah? Yeah, so there are many ways you can set a timeout. In this snippet of code is actually not that easy because it's like a built-in something into the JDK. So what I'm proposing at first, it's really hard to do it with one hand. So what I'm really proposing at first is just to create a thread pool. So here you have it. I'm creating a thread pool of 10 threads, and it sort of works. So I'm pretty sure you all know how it works. Rather than calling code directly here, I'm wrapping it in a callable of type string, which basically means I have a task, I'm wrapping this task, and it's supposed to return something of type string. That's cool. So what I'm doing next is that I'm submitting this task into a thread pool. This is Java 101, so I'm going to be really quick here. So I'm submitting something into this thread pool, and then I'm just like waiting at most 1 second for the response. And this is a crucial part, because rather than waiting forever for something, rather than waiting forever for this task to run, I'm just waiting at most 1 second. Of course, this task still keeps going in the background, There are things like cancellation and all this stuff, but let's just skip it for now. But at least I have this soft guarantee that my code is not going to block forever. It's going to block for at most 1 second. However, there are many actually issues with this. I haven't actually seen many examples in the internet that create a thread pool in a different way. So most of the samples you will find in tutorials are using this factory method. And this is pretty bad if you're doing enterprise software. Do you know how a thread pool actually works? It consists of 2 parts. The core one is a thread pool, so it's like a bunch of threads that are just running the tasks. But there's a second crucial piece of infrastructure. Do you know what is it? A queue, fantastic. So you probably also know what is the maximum capacity of this queue in this example. Yes, it's unbounded. So if you create a full thread pool like this one, we can actually go to the source code if you don't believe me, and it will actually tell you how to change it. So this is the source code of this class. It creates a linked blocking queue which is unbounded. And why is it a problem? Well, imagine you start submitting download tasks many times, and it takes much more time than it used to, for example, minutes. So what you do, and imagine a frustrated user that just presses F5 all the time because the website is not working, and we do it all the time as well. So this thread pool becomes saturated, so we get more and more tasks queued up, and suddenly we get out-of-memory error in our application. So how frustrating is that from our perspective? There's a system that becomes slow somewhere in the internet, in the cloud, and it's our application that fails with out-of-memory error, which is completely unrelated. And the exception, as you know, it's not even an exception, it's throwable. So this error can actually appear in a different place in the code because we have no guarantee that it will appear in the submit stack. So this is like a very poor man's solution, and there are many other things that are missing here. For example, we would like to have a lot of metrics. Metrics are the buzzword these days. So we would like to know how many threads were actually occupied, were busy throughout the time, so that we know what is the utilization of a thread pool. We would like to know what was the queue length over time, so to know like how many tasks were queuing up. We would like to know what were the average response time, what were the average execution times of tasks in this thread pool. So all the stuff that is really valuable if you're actually running this code on production. So you want to know what's the reason of slowness. And there's one more thing that is like really clever, and it's really hard to implement by yourself. So imagine you're running this code and you somehow figured out that for the last 10 seconds the code just kept constantly failing. So you've been like collecting some metrics or looking at just exceptions, and you see that no matter how many times you execute the download task, it just keeps timing out. So every single time you're executing download task, you get timeout exception after 1 second. So you can rather safely assume that if I run this piece of code again after hundreds or maybe thousands of timeouts in the last couple of seconds, I can rather safely assume that it is going to fail as well if I call it the next time. So I would like to have this nice property that the system somehow automatically figures out that something is going bad. So rather than executing this task again, even though I know it's going to fail, rather than executing this task again, I'm just going to like skip it entirely and just fail immediately. So this pattern is called fail fast. If something is supposedly broken, I'm just not going to call it again anymore because I know it's broken. So there's just no point waiting yet another second. I know it's like not working. Is it clear? Okay. So this is called fail fast. It's implemented in Hystrix. That's why I'm mentioning it. And let's see some examples. So this is the basic Hystrix API. Rather than using callable this time, let me just scroll it up a little bit. Rather than using callable, I'm using Hystrix command. So it's just a matter of changing a class from callable to Hystrix command. Don't bother about the constructor yet. And we have a run method that does pretty much the same thing. So it wraps anything that can potentially be unsafe in terms of performance, in terms of execution time, and so on and so forth. Basically, everything that's untrusted, so calling an external API, a database, a network file system, whatever, you wrap it in a Hystrix command. And what you do with it, well, it's actually much simpler. You basically create an instance of it, and every time you want to run this command, you create a new instance. It's a throwaway object, and you execute it. So I'm not really doing any assertions, just to show you the API. After executing a command, you get a string in return. Why? Because the command is parameterized with string. So this works, believe it or not. This works more or less the same as a thread pool we have in the previous example. So with every Hystrix command, or to be precise, with every type of Hystrix command, where type is basically a class of the command, with every type of Hystrix command, there is an implicit thread pool associated with it. So every time you call execute, you actually run this command in a separate thread pool. And Hystrix adds all these features that we were talking about. So first of all, we have a guarantee that this will complete within 1 second. This is the default timeout for every command we run in Hystrix. Excuse me? This is blocking, yeah. We'll show later how to, or actually I'll show it immediately. So rather than execute, you can call queue, which returns a future, or you can do observe, which returns an observable, if you know what RxJava is. But let's get back to execute. So this is blocking. It blocks for at most 1 second. And you have all these nice properties that we were talking about, like metrics, failing fast, and so on and so forth. But we will see that in a demo in just a second. OK. You won't imagine how hard it is to press Alt-Home with just one hand. Yeah. So I told you that the default timeout is 1 second. Actually, there's a constructor in every command, and this constructor will just keep growing and growing because it allows you to, zooming up, it allows you to configure Hystrix in various ways. Here I'm just showing you a basic parameter called timeout. So this means that if you call execute this time, it will block for 5 seconds rather than 1. So that's like an easy stuff. OK, does this out? No. OK, so I think it's about time to actually show you some demo. Not sure I'm going to do this with a microphone, but I guess it will work. So this is in Spring MVC, but it doesn't really matter. It's like a simple logic here. So I have a very simple web application that has 2 endpoints. And this is going to be really, really important. So listen carefully. So one endpoint is called nsave. So it's going to be available under /nsave when we run the demo. And this one calls some external service, whatever it is, directly. We will learn later what these params mean. They are useful for the simulation. So the idea is that external service tries to simulate some external dependency that misbehaves in different ways. So we can control how much time does calling external service take with some standard deviation, and we can control how often this service throws an exception. So this one simulates something that we call over the internet, which has latency, which has some positive response time, and it also simulates errors. So if there's a failure in this external dependency, we can actually see these failures popping up. So this one just calls this service directly and without any extra thought. And we have a second endpoint, which is called save, a different one. And this one, in contrary, actually does the same thing. So it also calls the external service with the exact same parameters. So from the business perspective, it does the exact same thing. However, this time, we are wrapping it in a Hystrix command with some parameters. It's not really interesting. So I have 2 endpoints. One is protected by Hystrix, called save, and the second one is not. And during the demo, we will see how they behave and what's the difference in the behavior. So let me just first run the application. Should take like 5 seconds, I hope. OK, so the application is starting up, and we will gonna use a tool called AB, a command line tool called AB. Do you know this tool? Yeah, it's Apache Bench. And for those of you who don't, do you know JMeter? OK, so if there's anyone not knowing JMeter, it's a load tool, like a graphical load tool that you just like put URLs and it slams your server with many requests. And AB is a command line, let's say, version of that one. So let's go to the terminal. OK, so do you see the terminal? No, not really. Okay, so I'm going to use AB, and it has like 2 parameters that are useful for us. So the first one is, I'm going to use keep alive. The first one is 1,000 requests. K is for keep alive so that the sockets aren't open and closed all the time. So the first one is number of requests that we want to run. 1,000 means 1,000 requests in total. And the second one is concurrency, let's say 10 threads. This basically means that we're going to execute 1,000 HTTP requests, and of course there's going to be a URL here. So we're going to run 1,000 requests over 10 threads in total. So on average 100 requests per thread. And here I'm going to just pass localhost 8080. So this is our application, the one that we just started here. It already runs. This is our application, and first I'm going to run /nsafe. And remember, I've told you that calling this external service actually has some parameters, and I'm going to pass these parameters right now. So the thing that I'm going to pass in the URL are actually the parameters passed to this external service. So I have a couple of tweaks that I can, with which I can adjust the simulation. Still see it? Almost. So the first tweak is duration. By saying duration, I can simulate that the external service takes some time to actually execute. So here I'm running duration of 100 milliseconds, which means every call to external service will take, on average, 100 milliseconds. And I'm adding a failure probability, another failure probability. It's been so long since I wrote with just one hand. Failure probability of, let's say, 0. Which means that every single call to this external service will actually succeed. However, it will take an average 100 milliseconds. So if I typed everything correctly, it should run right now. Yeah. So the test runs. I can actually interrupt it at any moment. It's a very useful, simple but useful tool. There are a few others that are interesting as well in that landscape. So I executed the test, and we have a couple of parameters. So the first one that's really interesting for us is this one. This is basically a median, not an average, but median. It tells us that 50% of the requests, we executed 1,000, 50% of the requests were faster or as fast as 103 milliseconds. So this was to be expected because this external service that we were calling sleeps. Actually, there's a sleep there inside call. It sleeps for about 100 milliseconds. And we have a distribution saying that, for example, 98% of the requests finished within 119 milliseconds. We have some long tail here, probably garbage collection or some other twitch happened, but it doesn't really matter. So response times are as expected, so the service just works and it works as expected. Another important factor that I want to show you is this one, failed requests of 0. Do you see it? Yeah. And this is also nothing really strange here, because our external service never really threw any exception. So we get the error rate as we supposed. Okay, so this time let's go for 0.8. Do you see it? It's very... Let me just zoom it up. Oh, poor idea. So for those of you who don't see it, I'm changing the failure probability from 0 to 0.8, which means 80%. Running it right now because it will take a while. So in this case, the external service still takes about 100 milliseconds to execute. However, 80% of the requests are going to fail with an exception. So in 8 cases out of 10, we're going to get an exception running out. So the response times are very similar. We still get 100-ish milliseconds. However, if we go slightly above, we get failed requests here and non-200 responses. I still don't know what's the difference between them. So I get 794 failures, which was to be expected. It's around 80%. It's like probabilistic. So nothing really strange happens here. So now let's switch into a safe version of our endpoint, and this time go back to failure probability of 0. So we have a second endpoint. You remember there was one called unsafe and the second one was called safe. Just as a reminder, the safe version, you see plenty of exceptions here because we were simulating them. I think it should actually say something like simulated, don't panic. So just to prove that there's nothing wrong happening here. Okay, so we have a safe endpoint here, which does exactly the same thing, just wrapped with Hystrix. So what's going to happen? Any bets? Any idea? Yep. Yes and no. So there was one answer that it's going to behave the same as unsafe, and this is not entirely true. I think someone was. No, we'll see. It will be slightly slower because Hystrix introduces some overhead. Very good point. But let's see. It's actually going to be much faster. But let's just run it. Why? Yes, exactly. So it's rather slow yet. I think the fail fast didn't work yet. Or I will just run it again and see how it behaves. Not yet. Yeah, so let's just run it again and see whether. Did I call actually unsafe? Ah, no, sorry. We were mentioning about fail fast, but we're actually running with no failures, so there is no fail fast here. Yes, so sorry for that. So it's working exactly the same, with the exception that it might be slightly slower. It really wasn't. It was like still 100 and something milliseconds. If you have a really, really busy server, it might actually, you might actually see some slow, some small footprint, some response footprint, but nothing really happened. So I actually cleaned the response. Let's stop it right here. So we have about 100 milliseconds response time by calling the safe version of the endpoint, and I believe there are no failures. So failure request 0. That works. So now what's going to happen, and this is what I was aiming toward, I increase the failure probability to 0.8, which means 80% of the requests are failing. And now we already know that there's this thing called fail fast, this pattern. In Hystrix, it's actually called circuit breaker, like the circuit breaker we have in our houses to protect ourselves from having too much current in the electrical wiring. So let me just run it and observe what happens with the request. I think you're going to actually immediately see it. Okay, so I'm going to actually run it again, and it's going to be even faster. So previously, just to show you, the previous responses were like, do we have it somewhere? Yeah, so 50% of the requests finished within 22 milliseconds, and then we have 100 milliseconds around 75th percentile. When I ran the test again, it was even faster. So 99% of the requests finished within 40 milliseconds. However, on average, it was actually much less. So what happened here? You already know because I explained it. There is this thing called fail fast. We're going to look in detail how it works. I mean, we're going to see all the parameters that control the behavior. So for now, you just have to understand that there is this pattern, and it actually kicked in some funky way. However, look here. We said that the external service should fail in 80% of the cases. But still, we executed the command 1,000 times. And according to AB, this benchmarking tool, it failed 1,000 times. So 100% of the requests failed. Now, you can probably guess that it's because the circuit breaker tripped open, which means all the requests were basically cut off. And it just stopped sending any requests to the external service, and it just failed immediately, even though some requests to this external service actually succeeded, or would have succeeded if we called it. So there's a trade-off here. You might ask yourself a question: is it a good idea to actually like entirely cut off of the dependency that somewhat works? And there was a research. And I think you can actually like tell it by yourself without making any scientific researches. There was a research that was trying to figure out, is it better to have a website that somewhat operates? So if you open it, it might work in 10, 20, 30% of the cases. Or you just like enter one page and it works, then you click a link and you just wait forever, and vice versa, whatever. So it just like looks really, really unstable, and it's just frustrating to work with. But it somehow works. So if you are really, really patient, you can get something from that website. So this is like one scenario. And the second scenario was just always showing, sorry, we are under maintenance, but immediately. So rather than having a website that works 10, 20, maybe 50% of the time, you just immediately, and in the other cases, you just get like slowness. It just does nothing. You just get a blank page and you stare at it and just keep spinning and nothing works. or you get an information that, sorry, we are under maintenance, or our developers are working on it. Everything is under control. And it turned out the probability that the people will leave the page and never go back is actually much higher if it works like 20–30% of the cases, even if it works. However, if you are like very clear about it, that we are working on it, that something is terribly wrong, but you just show this information immediately so that people are not frustrated waiting for it forever, they will come back because they know that the situation is under control. And this is where Hystrix really shines. If you're running a website, or if you're having a web service that should respond within a given amount of time, failing fast is a good thing. Because rather than propagating failure through all these layers, you are just immediately sending a signal that something is broken. There are cases where Hystrix doesn't work that well. Maybe you do want to continue the work even though it's like very unstable. You can just retry over and over. But this is how Hystrix works. So this is the basic idea of it. So I think we are. Yes, we are going to talk about it. I don't see who asked, but very good question. So is there? Oh, sorry. So the answer was yes, and the question was, is there any way to recover from this situation? And of course there is. Okay, so let's run yet another demo. This time I put back failure probability back to 0, which means the service is not going to fail. However, let's increase duration to 1100 milliseconds, and the default timeout is 1 second. So if we do unsafe call here, it's just going to return within 1100 milliseconds and nothing's going to happen. If we go for a safe version, even though the service works, however, it's slower than we originally anticipated, and of course there has to be some margin so that you're not failing too fast or too often. So if we go for duration of 1100, it actually stops, or it actually fails immediately, because Hystrix figured out that something is going wrong, and it's not going to call this command, even though it succeeds, but it just takes too much time to succeed, so I'm not going to call it anyway. It's too slow. And just to have like a trailer of the next slides, if I go back to 100 milliseconds, so an acceptable timeout, and if I go back to failure probability of 0, so no failures, or I can even go for like 0.1, which is like too few failures for the circuit breaker to actually trip open. We'll see later how it works. So if I go back to, say, normal situation and run the benchmark again, you see that the requests aren't that fast anymore. So the circuit closed. So Hystrix figured out that, okay, I think the system recovered. I think everything is fine, so I'm going to call this command again. So there is a logic built in, and it can actually close itself back. But we will see later how it works. Okay, any other demo that you want to check out? Please wait until dashboard, because we're going to see a lot of monitoring here. Okay, so we saw a first demo. So I promised to explain how circuit breaker works. And rather than going through the API in a boring way, I'm just going to give you some story. That's how it actually works. So all of this you see here, let's just put it up a little bit. So this is a command with a circuit breaker configured. And all you see here, every parameter you see here are actually defaults. I'm going to explain all of them in just a second. Everything you see here are defaults. So if you don't set up anything, you're going to get the same behavior as you see here. So we have a command. And first of all, we are collecting, by the way, look how epic method name. So it's with metrics rolling statistical window in millisecond, excuse me. I think I saw a question, okay. So it basically tells us, it's descriptive, come on. So what this method tells us is that Hystrix is going to collect last 10 seconds of statistics or metrics, whatever they call it. And by metrics, they mean how many commands of this given type, because we can have many different commands running in the system, how many commands executed within the last 10 seconds, or this parameter. How many commands failed, how many commands timed out, and so on and so forth. So it collects a lot of data about the actual execution of the Hystrix commands in order to apply the circuit breaking logic. So we have last 10 seconds of statistics, and this is a sliding window. So With every second, the oldest second is dropped, and the new second of statistics is being added. So we have last 10 seconds of statistics, and circuit breaker is enabled. Again, these are all defaults, so this is just for your discretion. So we have a circuit breaker enabled, and if more than 50% of the requests within this 10-second sliding window of statistics fail, if more than 50% of Hystrix command fail, and there are more than 20 executions in total, so within 10 seconds, more than 20 executions and more than 50% of them failed, then the circuit trips open. And by tripping open, I mean no execution of command, the command is not going to be executed anymore. The Hystrix will just immediately throw an exception saying, sorry, this command is, the circuit breaker for this command is open, so I'm not going to call this command anymore. I'm just going to slam you with an exception immediately, and there's no chance you're gonna see this, running this command anymore. So basically, this logic here is going to be entirely cut off. It's never going to be executed again, or not entirely true, because this would be really dumb if the circuit breaker would open permanently, and you would have to like restart your application in order to close it again. Hystrix would not be as dumb. So there's a third parameter with circuit breaker slip window in milliseconds of 5 seconds, again a default. And it would be really naive, and this is not how Hystrix works. It would be really naive if Hystrix would simply close the circuit after 5 seconds again. And by closing a circuit, I mean assuming that the external dependency works. So I'm just gonna like close the circuit and call it again. And if it doesn't work, because there's like a bigger failure like restart, or maybe we have a network partition or whatever, this is not gonna be something that we're gonna recover in a couple of seconds. If it failed, then we're going to collect these statistics and open it again, and then close it after 5 seconds, and then open it again. This would be really terrible, and this is not how it's implemented. There's actually a much smarter mechanism in place. What it does is, after 5 seconds, the circuit goes into so-called half-open state. In this half-open state, it will execute a single command, like a probe or like a scout that goes to the external dependency. So one user request will actually gonna be fulfilled. We're actually gonna be executed. And in the meantime, all the other requests are still being cut off immediately. So all the other requests are failing fast, except this single request once every 5 seconds. And again, there's a heuristic here. If the single request succeeds, we assume that the external dependency works. So we're going to close the circuit. If it failed, we wait another 5 seconds. Are all these parameters clear? Okay. This is like the core mechanism in Hystrix. So you should definitely understand it before applying it. And I don't think I emphasize it. A failure is when a command throws an exception or when it times out, the 2 error conditions. Okay, so that was it about circuit breaker. One important note about throttling. So I've told you that there is an implicit thread pool associated with every Hystrix command, with every type of Hystrix command. This is slightly simplified, but doesn't matter. So these are not defaults. The default size of a thread pool in Hystrix is 10 threads. Here I have 4. And the default queue length in front of this thread pool is actually, you're not going to believe it, 0. So Netflix, throughout their experience, figured out that 10 threads is actually enough for every single command to be executed. So it's like you don't really create thread pools of 100, or even I saw a thread pool of 1,000 threads in one application. They figure out that 10 threads is enough to handle their traffic. They're not really a big company. They're just like responsible for 30% of the internet traffic in the US. And still they like think that 10 threads is enough. Sometimes they use 20, sometimes 5, but this is like the sweet spot. And they don't have a queue in front of that thread pool. So if all threads are occupied, then you just like they are just immediately rejected. And we're gonna see later what rejection means. So These are the defaults. Of course, you can change them, but just think carefully before applying them. No, I mean, every command takes one thread, so you can execute 10 commands concurrently. No, actually, you have a command call. So the question was how the threads are dispatched between commands. So every command is wrapped in a class. So here we have a class called pooled command. And by default, you're going to have a thread pool for a class type. So if you have command 1, there's going to be a thread pool of 10 threads for that command. And if you have command 2, there is going to be a separate thread pool for command 2. And all the executions of command 1 go into one thread pool, and all executions of command 2 go into another thread pool. Is that clear? Cool. Okay. So I'm not going to tell you much about semaphores. It's not really that interesting. So there's like a really, really cool feature of Hystrix called streaming statistics, or whatever it is. Excuse me? Event stream. Thank you. So the idea behind event stream is that Hystrix has to collect a lot of data about the running system or about itself, like how many commands were executed, what was the error rate, and so on. This is this 10-second statistical window. And it would be really selfish if Hystrix would just keep this information for itself. And luckily, there's an API that allows you to expose these statistics and actually look inside Hystrix to see like how many times this command was executed in the last 10 seconds or whatever you set up this window. However, it actually gets way cooler. There's a built-in servlet that by convention you bind under this address. There's a built-in servlet in Hystrix that just comes with a library. You can set it up in WebXML or whatever you use. And this servlet streams data in real time. Let me just try to show it. Okay, I will leave the mic for a second, sorry. Okay, so our application optionally can expose this endpoint called Hystrix stream. Of course, the URL is arbitrary. And if I run it now, look carefully what happens. It's not just one, okay, you don't really see it, but the data just keeps flowing. So it's not just one response that we got, it's like many responses that we get over and over. And in order to see it, I'm actually going to decrease the font size insanely. I know you can see it, it's not the point. So running this again, and you see that the data just keeps flowing and flowing. So like I think a couple of times a second you get a new batch of data. Let's run it again. So a few times a second you get a new batch of data, and this data is actually really useful. So let's zoom again a little bit. Yeah, very good question. So the question was, does streaming the statistics break the performance, and does it impact the performance? Of course it does, because it's yet another thread that runs in the application. However, there's actually a built-in threshold that you are not allowed to connect with more than 5 clients into this endpoint. And we'll see later why it matters and how it can be mitigated. So yes, there is a performance penalty, and no, it's not really that big because not too many people are allowed to connect to it. Excuse me? Again, very good question, and I have a slide for that. Or if I don't have time, I will just answer you later. So the question was, is it possible to persist these statistics rather than have them like very temporarily? So, I mean, you can just look at this JSON, parse it yourself, and put it in a database like Cassandra or Graphite or whatever. But there's actually a built-in solution for that to like have more statistics. Okay, so we have this data, and if you look closely at this JSON, it actually has a lot of useful data, like is circuit breaker open? False. So it was fine. We have number of successes. We have response latencies. Basically everything about every single running command in the system, every single metric. So it would be really useful to build some sort of a tool, like a monitoring tool or some alerting tool that would just grab this data, read this JSON in real time, and do some alerting, statistics, whatever. So someone told that there's already a tool, and yes, there is. It's called Hystrix Dashboard, and it's part of the Hystrix distribution. It is released. I'm actually running it right now. So if you just clone Hystrix, there's a tool called Hystrix Dashboard. It's almost purely JavaScript application. We're going to see it in just a second. It's basically a web application that you start up somewhere. And it can grab this JSON, so this extra application that we're going to see in just a second. I think it's running, yeah. So it's running under localhost 7979. Not this one. Okay. So localhost. So I executed a web application that comes bundled with Hystrix. It's under 7979 Hystrix Dashboard. Here's how it looks. So again, this is an open source application that is part of the Hystrix distribution. And now let me zoom a little bit. Maybe too much. So it actually tells me to put some URL here. Do you know what should I put here? Okay, so what happened here is that I typed in the URL of the Hystrix stream, so this JSON that just kept flowing into our terminal, and see what happens. So we have a dashboard that looks very static. Let me zoom it in a little bit. So we have a dashboard that looks very static, and you have to believe me for now that it actually renders some data. And this dashboard reads JSON from the statistics stream that we exposed in our application, so it connected to our application. It reads this data about every single command. You see we have /save here, so this is one of the commands we have in our application. It reads this JSON and visualizes it, but because we don't have any load on the system, it just does nothing for the moment. So let's run some simulation. Okay, so this is our dashboard. Okay, so I'm going to run a simulation calling safe endpoint with a duration of 100 milliseconds and a failure probability of 10%. Are you still following what's going on? Cool. So nothing happens yet. Nothing happens yet. The dashboard is completely empty. Let's run it. Where's my... Okay. Here. Interesting. If I have a full screen mode, not everything is displayed, but... Okay, computers. Okay, so I'm running the simulation again, and I want to be really sure that you see. Okay, nothing happens right now. Running the simulation, and I'm going to be really quick here. So this was instantaneous. I run the simulation, and in the exact same second, I actually got a visual effect on the dashboard. And there are a couple of numbers. By the way, the benchmark, the AB load tool finished. So we already see that something is something went down. So let me just run this test again, this time with much more requests, so that I have some nice background when I'm talking. Okay, again, execute it, and we immediately see that something is going on. Okay, so there are a couple of numbers you see here. First of all, the green one is the number of successes within 10 seconds. So we have to divide it by 10 to actually see how many requests were executed. You also have a red number, which is the number of failures. So how many times this command failed. And it's actually almost perfectly in line with what we requested. We have 9% of failures. We requested 10. So it's about what to be expected. And all the others are 0. If we have time, we're actually going to run a demo to see all the other numbers being much bigger. And you can see this is the history of throughput, so how many requests were, so how many commands were executed over time. And the size of this bubble, do you see it? Yeah. So the size of this bubble expresses the load in this particular moment. So it's a nice visual effect showing you like what's the current load. And you also have statistics of a thread pool, so how many threads are currently busy, what's the queue size, and so on and so forth. So this is extremely useful. Let's just play with it a little bit. So I'm stopping the benchmark now, and you immediately see that the system goes into a halt and nothing really happens with it. It will take about 10 seconds to zero all the numbers, because this is the length of the statistical window. So what kind of test do you want to see first? What kind of benchmark? Nothing, some failures, something. So I'm going to choose for you. So rather than having 0.1% of the failures, so 10%, let's go for 80%. And in this case, we expect the circuit to actually open. So remember, we were just like looking at Apache Bench and trying to figure out, well, this is probably caused by a circuit breaker. There's something probably happening underneath. So now we actually have a dashboard to monitor everything. So nothing happens yet. So it's completely flat. And I'm running the test now. And something goes on. And yeah, now you see it. So this is what we call a fail fast. We actually see that rather than having 80 requests per second, we now serve almost 1,000, or it's more than 1,000 right now, because the application fails fast. So it can instantaneously tell us that something goes really, really bad. And look here, we don't have any successful request. Oh, something interesting happened. I'm going to explain it in a second. So we don't have successful request, almost any. Remember, 80% failing, not 100%. And most of the requests, the blue one, were short-circuited. And the idea is that since all the requests were short-circuited, none of them were actually getting executed. So the green number is 0. And you now see what's really the point of this this background, this bubble, because even if I take off my glasses and look at this dashboard, I can still tell that something is like terribly wrong on production. So, but now I want you to explain why we see a number 1 or 2. It should be 2 most of the time here. It's the number of failed requests. I actually explained it, so if you were careful, you should see it. Awesome. So the answer was, and was brilliant, so let me just wait a little bit until it stabilizes. Yeah, so the idea is that we have a statistical time window of 10 seconds, but every 5 seconds we are sending this one probe request. Remember, the scout that actually goes to external system to make sure it's still broken, or maybe it's recovered. And we see 2 requests within 10 seconds because every 5 seconds there is 1. So there should be something like 1 or 2. And the other thing you can see is that sometimes it actually goes back to the green state. So sometimes the circuit closes. And this is to be expected, right? Like now. And this is to be expected because this single probe actually hit this sweet 20%. So we send this one request to an external system. And it so happened that in this particular run, the external system succeeded. So Hystrix assumed that since one request succeeded, we just hit this 20% thing. Since one request succeeded, the whole system has to be working. So it closed the circuit and it pretended, or Hystrix just thought that the system is working. However, it wasn't. So it just like, it was failing. And it just keeps on and on. If the system, the external system, was completely down, so the error rate would be 100%, you wouldn't see this behavior. It would just be closed all the time. And circuit breaker is a really fantastic pattern for both sides, for the client and for the server. From the client perspective, you get this nice fail-fast behavior, so that you are not really waiting for an external dependency that you know it's not working. You can just fail immediately and it just works. However, from the server perspective, so from the perspective of the guy you are calling, it's also really cool, because rather than slamming the external system with requests, and if you have a website, for example, and something goes bad and the website is slow, as I already told you, you are just going for F5, F5, and F5, and you don't really wait for the first request. You just over and over and over repeat because it might work. So what happens is that you are actually doing a distributed denial of service on your own infrastructure using your users. So rather, just to avoid this situation, you are just cutting off the malfunctioning dependency because maybe it's just having a hard time. There's like a garbage collection running, or a restart, or maybe one of the queues filled up. So rather than slamming the dependency, like kicking the dependency even more, we're just cutting it off and saying, you know, bro, I know you're having a hard time, so I'm just giving you like 5 seconds. I hope you'll recover in that time. If not, I will give you 5 seconds more. But it allows us to have a distributed system that heals itself rather than collapse in case of a single failure. So rather than having a system that just falls out completely if one of the dependencies goes down, we allow this dependency to recover, and then maybe something will work later on. Okay, I think we have enough of this test. And sorry, can you wait a little bit? Yeah. Yes, of course. So the question was, is it configurable, all these parameters? So we saw this example. And all these parameters that are triggering a circuit breaker are actually explained here. So how many requests, the error threshold, the statistical window, and so on. So I think it should work now. OK, cool. Great. So by playing with these parameters, we can actually tweak circuit breaker or even turn it off entirely. OK. No, just one request is enough, but there's a parameter that tells us that we should check this one request every 5 seconds. So this is the one. Excuse me? Yeah, OK, there was a question there. OK. It's really weird because I feel like I'm talking in 2 different rooms. So I'm just going to stand here for a while, OK? Can you trust me? Oh, there's a camera there. OK, so I'd rather sit in front of the camera, sorry. Yeah, I'm a bad person. So the question was, is it possible to store these statistics somewhere so that we can look at them later? By default, or by actually it's by design, you don't, because Netflix is claiming that you can have both a lot of history and real time. So they just have like a dashboard that's the duration of 10 seconds, and you're putting it in a TV screen in your developer room, and that's like enough. However, this is not entirely true. So I'm not going to show this demo to you because we're slightly running out of time. But just to tell you that it works, I would have to show you like the dependencies. So basically, you can stream these statistics using, you see there's a Netflix Hystrix dependency called Hystrix CodaHail Metrics Publisher. And this is like a bridge API that takes statistics from Hystrix and publishes them to DropWizard metrics or CodaHail metrics. Do you know this library? It sort of works. So Hystrix publishes the statistics into CodaHail metrics. So this is like one step in the chain. And then you use metrics graphite module that takes the statistics from CodaHail metrics or from DropWizard metrics and publishes them to graphite. So you actually have like 2 dependencies that you have to put in your application, and almost with no code. By the way, all of this is on GitHub, so you can look at this application and everything is configured. So with just 2 extra dependencies and I think 1 or 2 lines of code, you can actually publish all of the statistics that come from Hystrix into graphite. And this works. Maybe we're going to have time for a demo of that. So it works, and it's possible. And we have it on production, and it works brilliantly. Okay, so the question is, can we limit the number of executions in a more gradual way? So rather than having a binary circuit breaker open or not, we like let 20% of the commands being executed. The answer is no, this is not supported. So either the circuit breaker is open and we don't let anyone, or the circuit breaker is closed and we let everyone. There are different tools for that. You can use toggles library, which allows you to like set up a toggle that's enabled just for 20% of the users. And the second thing is that if you have a distributed system, then you will have multiple instances of your application, and some instances will have a circuit breaker open and some will have a circuit breaker closed, which is like a poor man's solution for that. Yeah, I mean, also remember that there's a thread pool associated with every command, so you have a throttling there, because you cannot run more than, by default, 10 commands concurrently. Okay, so I think this answers your question about storing statistics in Graphite, or storing them basically anywhere. There are a couple of other features that I want to show you. I don't think I have a demo for that, so I'm just going to talk a little bit. So there was a question, a really good one previously, or some time ago, that was asking what's the performance penalty of streaming the statistics. Of course, there is some. I haven't really measured it, but definitely there is some overhead in that. And to avoid a situation where every developer connects to a production server and streams statistics to his or her computer, there's another project from Netflix, open source again. It's called Turbine. And this is basically a stream aggregator. So the idea behind Turbine is that you take a lot of applications. Maybe you have your application deployed in multiple instances on many servers. And rather than looking on the dashboard of every single application separately, you set up Turbine and you tell Turbine how to connect to every single instance independently. So you can just have a fixed list of addresses, of Hystrix stream addresses, or you can have some discovery mechanism that is pluggable. And in this case, Hystrix will, the Turbine will connect to every single instance of your application just once. It will fetch the statistics of every single instance, and it will create one single stream that's gonna aggregate all the data into a single one. And this is really awesome because rather than having a view on every single application alone, or every single instance of horizontally scaled application, you get a single dashboard for all instances at the same time. So for example, you see how many requests were executed in the whole cluster rather than how many requests were executed in every single application alone. I think I have a screenshot for that. Here it is. So this is a dashboard that's from the Hystrix documentation from Netflix. This is their production dashboard. So this is how it looks in their production. And if you look really closely, I don't think it should be visible. So they have something like 5,000 requests, 5,600 requests per host. So this is how many requests on average every single instance handles. However, in the whole cluster, they have more than 3 million requests executed per second. And if you look really closely, you have a metric here saying that they have 565 nodes in this cluster. And this means that this dashboard doesn't come from an application, it comes from Turbine. And Turbine independently connected to every single instance out of this 500-something applications. It grabbed the statistics from all of them and it combined them so that you get a single uniform stream of data. And then you can see like what's the behavior of the whole cluster. You can still connect to every single machine, but you have an overview of how the cluster looks like. So it doesn't really like mitigate the problem of performance penalty of streaming the statistics. However, at least you have just one consumer of for every application rather than multiple consumers split across developer machines. Okay, I think we have time for one last feature, or maybe two. So one feature is called caching, but this is a different type of caching that you would expect from caching solutions like EHCache, Hazelcast, or whatever. So if you have a command, a type of command, let's say cached command in this case, there's a method that you can override called getCacheKey. And this one is supposed to return some unique key that identifies this instance of the command. So this is actually a bad example. It should return something like an ID. And this ID is, for example, an ID of a person that you are trying to fetch with this command. So let's say you have a client that tries to load a person from a database with ID 17. So you're creating a command, you pass 17 as a constructor argument to this command, and then you are returning it as a cache key. So the idea is that if two clients at the same time are asking for the same cache key, so two people at the same time are asking for the person with ID 17, Hystrix is smart enough to figure out that two people are asking for the same thing. So it's going to execute the command just once, and the response of that command is going to be dispatched to both clients. So there's like a bit of blocking here, but we avoid extra load on the server side. And this is a cool thing. Other caching systems like EHCache or Hazelcast can do it, but there's like an extra work that has to be done. So this is not an ordinary caching. It's just a way of mashing up together same requests. Is this clear? So this is like just a warm-up to another subject, the last one, called batching. And I urge you to actually look at the source code because it has a full implementation, but what I'm going to show you is just like the general overview. Let me just find an interface. So if we have two exactly the same commands executing at the same time, this is simple. We can just execute it once and then dispatch the same response to two clients. Obviously, if they don't have some side effects. However, imagine you have two commands that are asking for similar pieces of data. Like one command asks for a person with ID 17 and a second command asks for a person with ID 18. So I have a slightly different example here. Let's say we're asking a stock exchange something, some API. We are asking about prices for different stocks. So a ticker is like IBM, Microsoft, whatever. And one client asks for Microsoft and a second client asks for IBM. So we have two commands. However, we are paying the network round trip penalty twice because we have to go, for the first client, we have to go over the network and go back, and for the second client, we have to do as well. So the API that we were given actually has a solution for that. Instead of calling, instead of paying this price for network round trip twice, we can call load many method, which is basically a batched version of the same command. So the idea behind it is that if we are asking about two different stocks like Microsoft and IBM, rather than calling the stock exchange twice, we can just like make one request for two different stocks and then return with a batch response. And when we get this batch response for two different stocks, we dispatch it back to the clients. So this is fairly understandable, right? It seems like a good idea. And it's not really that much more work on the server side to perform, to make two requests, to handle two requests versus one, but we have less latency on or actually bigger throughput. The problem is that imagine you have two threads in your application, two entirely different clients. And one thread, one client asks for Microsoft and the second client asks for IBM. And you have to somehow figure out that these two clients are asking for different stocks, more or less at the same time. And you have to somehow correlate these two commands so that you just make one batch request. So imagine how the implementation would look like. You would have to like have a lot of synchronization here, maybe some micro caching so that you see that one request was already here, so I have to wait for the second one. This is just damn complex. It's possible to implement, it's just really complex. So Hystrix allows you to do it out of the box. Luckily, it's not using reflection or some other magic. You still have to write some code. But all the infrastructure that you need for that, so like correlating different commands so that they are in line with each other, this is done by Hystrix. So the full source code is there if you want to look at it. It's quite, well, maybe not complex, but it requires a lot of time to explain. But the basic idea is that if if two commands come in, one for Microsoft, second one for IBM, or maybe two for IBM at the same time, Hystrix is capable of merging them together so that we get just one big command. And when this big command comes back, we dispatch the results to all the awaiting independent requests. There's one trade-off here, one really big trade-off here, and maybe if you like got the idea, maybe you understand what it is. Can you guess? Yes. So I told you that I said something really unrealistic. I said that if two requests are happening at the same time, which is not true because there is no such thing as at the same time. So the idea is that when the first request comes in, Hystrix actually has to wait a little bit. By default, it's 10 milliseconds, because maybe another request will come by so that it can be merged. But maybe another request will not arrive. And what we did, we just introduced 10 millisecond sleep into every single request in our system. So batching is extremely powerful if you want to flatten out peaks of load, and if it's possible in your system, if you can do batching. However, it's a double-edged sword, and if you don't have such a big load that you have hundreds or maybe thousands of commands per second, it will just add you an extra latency without any benefit. This was the last example. I don't think I have more time, so it was a pleasure to talk to you. Thank you.